welcome to the final session of Unit 3. And this final session, we'll be looking at force concept. My name is Patrick Ej. Now, at the end of this session, you should be able to demonstrate an understanding of the relationship between force and motion in 1 and 2 dimensions. Then you are also expected to develop and interpret free body diagram for force analysis. And finally, you should be able to draw and label correctly a free body diagram representing situations where forces are being applied to an object. Now let's look at force. Now what is force? What is force? And basically when we mention force, the simplest answer you are likely to say is that it is a push or a pull. So that if the force is great enough to overcome friction, then the object that is being pulled or pushed is going to move. And for that reason, we can also say that then a force is something that is able to make objects move. So actually, if we are saying that force is something that makes objects, then force gives rise to acceleration. And the acceleration of a body is directly proportional to the net force that is acting on a body. And when we make mention of the word net, it is important to mention it because forces are vectors. We know a force is a vector. And for vectors, we know a vector has magnitude as well as a direction. And whenever we are finding the net or the sum of forces, then the sum must be done vectorially, in that we must add them based on their components. And so the net force basically talks about the vector sum of all the forces that are acting on a body or on an object. And the unit of force is the Newton with the symbol capital N. So let's take note of that. Now let's look at force diagram. Now we mentioned that the net force or the resultant force acting on a body is the vector sum of all the forces that are acting on that particular object. And it is also important to remember that all the forces must be acting on the same object. So we have one object and we have several forces acting on this object. And the easiest way we can determine the resultant force is to construct what we call the force diagram. And in a force diagram, we represent the object by a point and draw all the force vectors connected to that point as arrows. And we use the length of the arrow to indicate the vector's magnitude and the direction of the arrow to show the direction along which the force is being acted. And the second step is to rearrange the force vectors so that it becomes very easy to add them together and find the resultant force. Now note that we rearrange them so that we can know the various components and we can add the vectors, because force is a vector, and in the addition we can only add components that are in the same direction. So example, two people push on a box from opposite sides with a force of 5 newtons, and we can represent this diagrammatically as, so we have force 1, that is 5 newtons, and force 2, which is also the same 5 newtons. But the arrows are telling us that these forces are acting in the opposite direction, and the length of the line is talking or showing us the magnitude of the force. And when we draw the force diagram, we are now going to represent this box by a dot. So two forces are represented by arrows with their tails on the dot as shown below. So over here, this is the box and these are the forces. Now we could observe from here that the force 1 is going in the positive x direction and force 2 going in the negative x direction. And when we come here, we can see the two forces acting on the body, which is represented as a dot in this case. So let's look at equilibrium of forces. And in equilibrium, we are saying that different forces are acting on the body. And once we have different forces acting on the body, then a resultant force would cause a stationary object or the body to start moving, or an object moving at a constant velocity to speed up or to slow down. That is, in other words, for stationary objects or objects moving with constant velocity, the resultant force acting on the object is 0. And when that happens, we will say that the body is in equilibrium. So when we have a number of forces acting on a body and the resultant of such a force is zero, then we will say that the body is in equilibrium. And if a resultant force acts on an object such that the object can be brought into equilibrium by applying an additional force, then that force will exactly balance the resultant force. So when we have a number of forces on an object and this number of forces are able to cause the body to be in equilibrium, when we add additional force, that additional force must still be able to cause a balance in the resultant force acting on the body. And such a force is called the equilibrium and is equal in magnitude, but it is opposite in direction to the original resultant force acting on the object. And so let's look at this example of the equilibrium of forces. So in this example, we have force F1 and force F2, which are being acted upon or which are acting on a body. Now the resultant of F1 and F2 is what is being shown here. And so F3 now becomes the equilibrium of F1 and F2. In other words, F3 is the force that can bring about a balance to the resultant of F1 and F2. And so in the figure, we said that the force F1 and F2 is the resultant, and the resultant is shown in the red color. And the equilibrium of F1 and F2 is the vector, which is opposite in direction to the resultant force with the same magnitude. And we saw that was F3. And so in summary, we can say F1, F2, and F3 are all in equilibrium. But F3 is the equilibrium of F1 and F2. In other words, F3 is the force that can balance the resultant of F1 and F2. And F1 and F2 are also kept in equilibrium by F3. Now let's look at this example. Now let's consider an object that is held stationary by two ropes in the arrangement that has been shown. So we have rope 1 and rope 2, and they are acting at different angles on the body. Now, in the force diagram, if we are using a force diagram, we said the object must be drawn as a dot, and all forces acting on the object are drawn in the correct direction starting from that dot. So in this case, we have three forces acting on the body. So this is the object, this is the first one, that is the tension and the first rope, and in the first rope we are going to get tension in it, which is a force. In the second rope we also have another tension in it, and the weight of the body, which acts vertically downwards. Now each rope exerts a force on the object in the direction of the rope away from the object, and these tension forces were represented as T1 and T2. And since the object also has a mass, it is attracted towards the center of the earth, and because it has a mass, it will also have a weight, and the weight is represented in the diagram as W. And since the object is also stationary, the resultant force acting on the object is zero. In other words, the three force vectors drawn tail to head will form a closed triangle. So when we say tail to head, you realize that this is the head of the weight, that is W, and it ends on the tail of T1, and T1's head will be the beginning point of T2. And we are now getting a triangle, a closed triangle formed by the three forces acting on the body. So in general, when the forces are drawn, said that we have tail to head, then the forces acting on an object in equilibrium will now form a closed figure with a head of the last vector joining up with the tail of the first vector. And when only three forces act on an object, this closed figure is a triangle, as we saw. And this will also lead us to the triangle law for three forces in equilibrium. And what does this law say? The law says that when we have three forces in equilibrium, then the forces can be represented in magnitude and direction. by the three sides of a triangle that is taken in order. A very nice law. So that when we have three forces acting on a body and the body is in equilibrium, then we can represent the forces as the magnitude and direction by taking the three sides of the triangle in order. In other words, the tail of one will end on the head of another force. In this session, students, we looked at the force concept. Now, as we bring this session to an end, let us have this as a take home. Now, we have been provided with diagrams A and B, also known as sketch A and sketch B. Now, you are to draw a force diagram to represent the forces acting on sketch A as well as sketch B, and determine the tension in the chain in